Okay, here's our function y of t equals a e to the square root of 6 it plus b e to the negative square root of 6 it. Here's our Euler identity, e to the I theta equals cosine theta plus I sine theta. What does this identity tell us about this solution? It tells us that e to the square root of 6 it is going to be the cosine of the square root of 6t plus I sine of the square root of 6t. And b e to the negative square root of 6 it is going to be b multiplied by the cosine of negative square root of 6t plus I times the sine of negative square root of 6t. Now the even odd properties of the cosine and the sine tell us that this is going to be a times the cosine of the square root of 6t plus I sine square root of 6t plus b times the cosine of the square root of 6t, the cosine being an even function. The cosine of negative square root of 6t is the same as the cosine of the square root of 6t. Sine, on the other hand, is an odd function, so we get minus I times the sine of the square root of 6t. If we distribute the multiplication and collect the real terms and the imaginary terms, it's easy to see that what we end up with then is a plus b times the cosine of the square root of 6t plus I times a minus b, and that's a really lame looking minus sign, I'll fix that in a second, times the sine of the square root of 6t. Now we can write this as d, well, I don't want d, magically change that to c times the cosine square root of 6t plus I times d sine of the square root of 6t, where c equals a plus b and d equals a minus b. And I note that these are two simultaneous equations that can be solved for any selected values of c and d. So whatever c we want, whatever d we want, we can find values of a and b that give us those values of c and d. So I'll just say that's solvable for any c and d, which means that we can make this solution equal to this for any chosen values of c and d, and we're guaranteed that this is still a solution to our original equation. And I'll go even a little bit further, and I'll say even for complex values of c and d. In other words, c and d could be any complex numbers. The a and b that would give us those complex numbers are probably complex numbers themselves. In any case, our conclusion is that this is a solution to our original equation, which was y double prime equals negative 6y. Okay, this equation has this solution where c and d can be any complex numbers whatsoever. We haven't talked about how to interpret these solutions if C and D are complex numbers, but we acknowledge that this is the case. If these are complex numbers, it doesn't matter. If I plug this back into this equation, everything works out. We get an identity. Left-hand side is going to equal the right-hand side. The real part of the left-hand side is going to equal the real part of the right-hand side. The imaginary part of the left-hand side is going to equal the imaginary part of the right-hand side. You don't need to understand the implications of that right now. Just store away the fact that it's so. We'll get to the implications shortly.